Oops. So I have a few more things to say, and then we'll see how far we go today anyway. I have a lot of examples, but if we run out of time, we run out of time. That's okay. All right. So your Chapter 34 homework is due on Thursday night. And like I said before, Exam 5 will have 3 problems. And some short answer questions, okay? And you know, the 3 problems will have multiple parts. And so just because it only has 3 problems doesn't mean the exam is gonna be shorter than the other ones. And just remember to study the homework problems that you've done for these 3 assignments, okay? Because at least half of the problems or parts of problems will be similar to the homework that you did, okay? So please make sure you understand, don't memorize problems, but understand the process that you use to solve the problems, okay? So I'm gonna say at least half of the problems are gonna be, or half of what you're gonna work on is gonna be similar to what you did in the homework, okay? Any questions regarding the exam?
What do you mean by short answer?
I'm sorry, it's hard to hear you.
I know I'm quiet again. I don't really know why. I played with my mic and it's still quiet. I'm not sure why. But what do you mean by short answer?
Well, like, or multiple choice. You know, I'll ask you a question and you have to explain something, or it's a multiple choice question, or you have to draw something, or, you know, something like that.
Okay.
Okay, that's what I mean by that. You know, they shouldn't take long, hopefully.
Okay, cool.
As opposed to the problems, you have to work, you know, you have to do a bunch of calculations when you solve a problem.
Yeah.
Other questions? Okay, so last time we began by talking about some properties of waves, okay? And this came from the solution to Maxwell's equations. Okay. Well, this came from Maxwell manipulating his equations and coming up with the wave equation, which I'm going to show you in a minute. The physics governing the electromagnetic waves is based on the wave equation. And what comes out of it is that we have these waves that can travel through space. The type of waves we're going to focus on are the waves that come from a periodic source, an oscillating source, because you see those a lot in nature. And what are some properties of these waves? Well, lambda is the wavelength. The speed of light is c. And Maxwell was able to actually theoretically predict the value of the speed of light. It's given by this expression. And t is the period. And frequency is 1 over the period. Omega is 2 pi f. And this is the angular frequency. K is the wave number. And omega over k is also the speed of light. And then we also have c is f lambda. So we've talked about these, and then we've also said that the direction of travel of the wave is perpendicular to both the electric and the magnetic field. So in fact, if you take the following dot products, let y hat denote the direction of travel of wave, then y hat dot E is 0, y hat dot B is 0, and E dot B is 0. It means they're all perpendicular to each other. Okay. Now remember that E and B are in phase, but their direction of oscillation are perpendicular to each other. Okay. And then E max and B max are basically the amplitude of the waves. In fact, E, B, and the direction of travel form a right-handed coordinate system. In fact, E cross B is in direction of travel of wave. And we'll find out that this cross product is useful for us. Okay, it actually has some physical meaning. We'll find out in a little bit.
Professor?
Yeah.
Can you hear me better?
Yeah, a little bit better now.
But I do have a question. So is the direction of the wave always the pointing direction?
Is the direction, you cut out a little bit, the direction of the wave?
Always the same as the pointing vector direction?
Yes. Yeah, and we're going to get to that. But yeah, it's so you saw that this is going to be related to the pointing vector. That's why we define it, because this cross product, which is the direction of the pointing vector, represents the direction of travel of the wave and the direction in which the energy flows. So you're right about that.
Okay, cool. Thank you.
Okay. Now, what is the equation that governs the properties of these electromagnetic waves? And it's the wave equation. And the wave equation can be derived under various circumstances. If we look at the case when we're real far away from the source, where we can say I equals 0 and Q equals 0, essentially, because we're far away from the source. And let's consider a wave traveling just along the x-axis. Then we can derive an equation that governs the wave. And the solutions yield these properties. And the wave equation for a one-dimensional wave looks like this. Oops. This is the one for the electric field, and of course this is for a wave traveling in the x direction only. And so the direction of the oscillation of the wave can either be in the y or z direction. Okay? The direction of oscillation of the wave has to be perpendicular to the direction of travel. And then we also have one for the magnetic field. It looks very similar. Now, mu naught epsilon naught is 1 over c squared. And so this is actually the simplest version of the wave equation. If I is not 0 and Q is not 0, then the wave equation becomes more complicated. And then the solution then would come from you solving this partial differential equation. Okay, so you'd have to go beyond the course of beyond Math 33 to learn how to solve these kind of things. There aren't that many partial differential equations that are solvable. Now, solving this, finding the solution to this is not easy. Okay, but this is the simplest equation. In fact, if this was a three-dimensional wave, then there would be two terms here on the left-hand side that had partials of E respect to Y and partials of E respect to Z. Actually, there's second derivatives of E respect to Y and Z. Okay, we're focusing on the wave that's just traveling along the X direction. What do the solutions look like? I'm not going to derive the solutions. I'm going to tell you what the solutions look like. They actually have this form. So solutions to the wave equation has the following form. The electric field is some function of x plus or minus the speed of light times t. And the magnetic field has some form that also depends on x and a product of c times t. Okay. How can I prove that this solves this equation? How can I prove that?
Plug it in.
Yeah, just plug it in, right, and use the chain rule and show that the left-hand side equals the right-hand side. That's the only thing, at this level, that's the only thing we can do. Okay, just plug it into there and use the chain rule and show that when you take the second derivative with respect to x on one side and you take the second derivative with respect to t on the other side, you get that the left-hand side equals the right-hand side. And you can see by using the chain rule, if you differentiate the right-hand side twice, c squared is going to come out of this. It's going to cancel out that mu naught epsilon now, which is c squared. Okay. Now, the positive sign, this is always confusing, is a wave traveling in the negative x direction. The negative side is a wave traveling in a positive x direction. Does that make sense or does that bother you?
Bothers me a little bit.
Okay, so let's do this then. Let's try to clarify why that's the case. Suppose I have, it doesn't have to be a light wave, it could be any wave. This is true of any kind of wave. You can flip the C into T, yes. So let's do this. I'm going to draw two coordinate systems. And let's just use let's do a mechanical wave, because the mechanical wave is not traveling near the speed of light or anything, like a sound wave. This is true for any kind of wave. I'm going to draw two coordinate systems, x prime and x. X prime is moving to the right with speed v. Okay, and let's focus on a point in this coordinate system. This coordinate, according to the moving frame, is x prime, right? This distance is x prime. Isn't that true? According to this person, who's not moving, how do you write that coordinate? In other words, what is that distance according to this person? What is the location of this point according to this person?
Wouldn't it be the sum of the two different distances?
Yeah, so let's assume a time t has elapsed. Then it's true then that x prime is equal to x plus, I'm sorry.
That x equals x prime plus vt.
And that makes sense. And of course, x prime is x minus vt, right?
Yeah.
Okay, so we're okay with that, right?
Yeah.
So now imagine this is you sitting on top of this wave. You're moving with the peak of the wave. The functional form of this wave is f of x prime, right? To the person in the unprimed frame, this wave is moving to the right, but you're sitting on top of the frame, so you call this function f of x prime. According to that person, f of x prime is the same as f of x minus vt because of this relationship. Isn't that true?
Yeah.
So wave traveling to the right, you have a minus sign there. Does that help?
Yeah, I think so.
Okay. So that's where it comes from. It's always confusing. And I think like when you guys do, like if you had, I think it's in pre-calc, they do things where they translate the coordinate system. You get something that, like this that happens too. So this is the general form of the solution to the wave equation. But for specific cases where you have a source that's very sinusoidally with time, your solutions basically involve sines and cosines. And so we can write the solutions for this special case where we have a periodically varying source in the following way. Couple things. One thing, a couple of things missing from here. What's missing?
Well, your bars on. Oh no.
I'm missing the direction. I'm missing a unit vector here, right?
Oh yeah.
So this unit vector has to be perpendicular to x. Okay. So I'm going to write a unit vector called E1 like this. It's a vector that's perpendicular to the x direction. Okay? And then I'm going to put another unit vector that's perpendicular to both of them. I'm just going to call it E2.
And that's just if the wave is traveling in the x direction, right?
Yes. This is just for a wave traveling in the x direction. This term here, the x in here in the argument of the cosine function basically tells you which direction it's traveling.
Okay.
What else do you notice that's different? Well, I have x, I have some function, b is some function of distance, right?
Oh yeah, there's a cosine.
And then here it's some, this is dimensionless because this is 2 pi over lambda, right? It's 1 over distance and distance. So, and in fact, you have to do that with trig functions. The argument in a trig function has to be dimensionless. And so you might say, well, this is different from this, but really it's not, because if you factor out the k, omega over k is c. So I still had that form here. This has to be in here because this whole thing has to be dimensionless. So when you solve it, when you solve the equation for this case, you'll find that this argument has to be dimensionless. Anytime you're dealing with a trig function or an exponential function, the argument, whatever you're raising it to, it has to be dimensionless. And you can prove that. You can prove that to yourself by taking the cosine function and expanding it in a power series. Because cosine function, it goes something like this. So these things have to be dimensionless, because otherwise you're adding something with dimensions to the second power plus something with dimensions to the fourth power. So this whole thing has to be dimensionless. So these are simple, and these occur, anyway, this form occurs often in nature. You'll see these forms used in 215 when we talk about optics. Okay, this is a common one, and this form can help us understand a lot of phenomena that we observe in nature. This form comes up when we're really far away from the source of some sort of periodically oscillating source. Okay? So suppose I came to you and I said to you, these two functions that you see here represent an electromagnetic wave. How would you know whether or not I was telling you the truth?
Did you just plug them into the wave equation?
Yeah, you just plug them into the wave equation. Good. All you got to do is plug those into the wave equation. Now, granted, they don't represent a periodic wave. In fact, you see the graphs of what those waves look like at different times. I plotted the graphs as a function of a position at different values of t. It's just a different type of periodic function based on whatever the source is. But yeah, you just plug it into the wave equation and show that the left-hand side equals the right-hand side, and then you know it works. Okay, so when we solve the wave equation for electromagnetic waves, we're able to get an equation where we can describe the wavelength of the wave, the frequency of the wave, etc. And by the way, there's really only two sources of electromagnetic waves, and I'll talk about those in a minute. The possible different wavelengths that we get form what's called the electromagnetic spectrum. And this figure that you see here describes all the different types of electromagnetic waves we have observed in nature so far. They go from very long wavelengths, which are radio waves, to very short wavelengths, which are gamma rays. Wavelengths greater than 1,000 meters is possible. Wavelengths smaller than 10 to the minus 12 meters is also possible. As the wavelength increases, the frequency decreases. Okay, and as the wavelength decreases, the frequency increases because c is f lambda. And what this picture shows you is the different types of electromagnetic waves. There's radio waves, microwaves, infrared waves. And infrared waves, they're observed, for example, our bodies emit infrared waves. And it's because of the vibration of charged particles in our body. Look at the smallest region of the electromagnetic spectrum. It's the visible. You see how small that is? It only spans 300 nanometers compared to all the other ones, which spans more than a factor of 10, more than a decade of wavelengths. And I'll write down in a minute what the visible range is. Anyway, infrared radiation, where does it come from? Well, it can come from a hot object that's radiating energy because of vibrations of charged particles. You can have the visible light, light from the sun. Part of the light of the sun consists of visible light in addition to infrared. Transitions in atoms produce visible light. Then there's the ultraviolet. Transitions in atoms also produce ultraviolet. Soft X-rays and hard X-rays, they can come from either transitions in atoms or the acceleration of charged particles. And gamma rays, which generally we denote gamma rays as coming from the nuclear decays. Notice, again, there's no border between what infrared and visible is. There's no definite border. In fact, some of these overlap. Look at the soft X-rays and hard X-rays, they overlap. In fact, gamma rays and hard X-rays strongly overlap. The only distinction between them is that hard X-rays come from, generally we say that hard X-rays come from accelerated particles. Gamma rays come from nuclear decay, but doesn't matter what the source is, really, they're going to have the same properties. We just name them just because of their source, that's about it. Any questions about the spectrum?
No.
So let me say something about visible light. Visible light something as a student you should remember for the rest of your life. Visible light is in the range of 400 nanometers to 700 nanometers. What's the range of frequencies? Well, remember that C equals F lambda, so we can calculate the range of frequency by taking C and divide it by 400 nanometers. You got to convert that to meters. And take C and divide it by 700 nanometers. It's in the range of 10 to the 14th or 10 to the 15 hertz. Okay? But this is a small range. Okay? And this is not a definite number. This is an approximate number. Okay? But this is usually the range that's given for visible light. And it's, it's more interesting to us, to human beings, is because we see in the visible range, we don't see in the IR. Okay? So the range of frequencies you can calculate by taking 3 times 10 to the 8th divided by 400 times 10 to the minus 9, and then 3 times 10 to the 8th divided by 700 times 10 to the minus 9. That'll give you the range of frequencies. So how are these waves produced? Really, there's only 2 sources of electromagnetic waves. One, electric charges oscillating or accelerating. Okay? If it's oscillating, it's accelerating. So any accelerated charged particles produces electromagnetic radiation. Like if you have electrons oscillating in a wire, if they accelerate at the right rate, then they can produce the frequencies for AM radio or FM radio. By the way, in physics and maybe chemistry too, sometimes they use the letter F. Most of the times they use the letter F for frequency, but sometimes we use the letter nu for frequency, as you see there in the slide. So you can either have accelerated charged particles producing electromagnetic radiation or transitions in atoms and molecules that produce electromagnetic radiation. And that includes the nucleus of the atom. And if you've had chemistry before, you've probably learned about transitions in atoms and molecules. And if you take 215, we'll have enough time to discuss briefly transitions in atoms and molecules. So how do you produce electromagnetic waves? And what happens? Well, that's a very difficult thing to discuss. The production of electromagnetic waves from accelerated particles, let's say in a dipole antenna, is complicated. And so I cannot really get into the math behind it. So let's say we have a wire with positive charges here, and it's split into two parts with negative charge here. And we'll let the charge oscillate. So this goes from positive to negative, and this goes from negative to positive. As the charge oscillates, an electromagnetic wave, an electric field is produced that goes outward. If this charge oscillates, then you have a current. And you know from Ampere's law that the magnetic field associated with this current is going to circulate, is going to actually form circles around the wire. And so you're going to have a magnetic field circulating around the wire, and then all the way around you have electric field emanating from it. Not just in this direction, but all the way around the wire. When you're really close to the source, generally it's between 2 and 10 wavelengths, the waves are difficult to describe. The amplitude of the electric field drops as 1 over r squared. So does the magnetic field. But once you get further than 10 wavelengths from the source, we're what's called a far field regime, then the electromagnetic waves feed off each other because of Faraday's law. The amplitude decreases as 1 over r. And the electromagnetic radiation has an appearance as you see on the screen. So far from the source, E max is proportional to 1 over r. B max is also proportional to 1 over r. So let me say something about this effect, okay? And this does make sense. We can try to make sense of that. Let me plot E max as a function of r. It looks like this. Okay? This is E max as a function of how far away you are from the source. Now, take a look at this part of the graph. Does this graph change much when you're really far away from the source?
No.
No, in fact, it's almost constant, right? So those plane wave solutions that I showed you, E cosine kx omega t, E is constant there. And because we're assuming we're really far away, we're making the approximation that this ain't going to change much far away from the source. Most of the change occurs real close, but when you're really far away, it doesn't change much. So we say, okay, we can still write but in reality, this decreases with R. If you're really far away, you're not going to notice how much that changes. If you're 1,000 meters away, and then go from 1,000 to 1,001 meters, I mean, this ain't going to change much. This is a figure that represents the amount of energy per unit area per unit time that's radiated from a dipole. The dipole is oscillating in the vertical direction. The blue represents the radiation of the light. So let me plot that on the board. Notice there's no energy radiated along the axis of the dipole. Have you seen a picture like this before? Oh yeah, and you have to do this over 360 degrees. You have to rotate over 360 degrees along the vertical axis. That'll give you a picture, a three-dimensional view of what's being radiated. Have you guys ever seen a picture like that before? In chemistry? Have you had chemistry? When you look at the various orbitals of the atom?
Oh, yeah.
Yes, P shells.
Yeah.
Okay. If you have a P to an S transition in an atom, the energy that's radiated looks like this, has this form. Okay? Because it's a dipole, it's dipole radiation that's coming from the atom. So it looks like this. Okay? Now, there's no energy in this direction, but if you want to look at the energy per unit area per unit of time that's radiated as a function of the angle between the axis of the dipole and some point here, you'll find that it's proportional to sine squared theta, and it's maximum, the energy is maximum perpendicular to the axis of the dipole. Right now, I'm just telling you some of the properties of the radiation for a dipole. I can't derive any of these equations for you, okay? The math is fairly complex. Since we've been talking about energy, let's look at how much energy flows through a thin box. Let's talk about the flow of energy when it comes to electromagnetic radiation. So I'm going to draw a thin box. And Didn't draw very well. Its thickness is dx. Its area is x. Its volume, dV, is a dx. Okay? And let's say we have an electromagnetic wave coming towards us out of the board or out of the screen, such that the electric field is oscillating this way and the magnetic field is oscillating horizontally. I can switch them, it doesn't matter. I want to know how much energy is flowing through that box. I want to know the rate in which energy is flowing through that volume, basically. I want the power per unit area. So basically, it's the energy per unit area per unit time, which we can write as 1 over A times du over dt, where du dt is the power. In order to figure this out, I got to figure out what du is. I need to write an expression for du. Okay. And I'll name what this is in a minute. du is the total energy density contained in the field times dV, which is going to be u sub E plus u sub B A dx. And so du dt is going to be my total energy what's dx dt?
Isn't that just C?
It's just C, that's right. And so 1 over A du over dt is going to be equal to that, which is the total energy density times the speed of light. And we can write this a number of ways. Because the energy is going to oscillate between these two. And yeah, let me call this S. I'll name that S. Now I can rewrite this because we know that B is equal to the electric field over the speed of light. I can eliminate the E from here, and I can get S is equal to that. Or I can write it in the following way. Using that relationship. Oops. So whatever this is, I can write it as E times B over mu naught. So the flow of energy per unit area per unit time is given by this expression. And the energy only flows, right? We can define, or the energy flows through the surface, normal through the surface. I can define a vector that represents the flow of energy. I'm going to define it this way. We call it a pointing vector. This is going to represent the energy flow per unit area per unit time, and it tells you the direction in which the energy is flowing, because this indicates the direction of travel of the wave. If I take the dot product of this vector with the normal to the surface, right, which is going to be, in this case, the direction of travel of the wave, I get the magnitude of that vector. I also get the energy flow that's coming through it, each surface. This is the pointing vector, and this allows us to look at the flow of energy. Now, the intensity of is basically the magnitude of the pointing vector. The intensity is the average power per unit area per unit time. A lot of times we talk about the intensity of a wave. Now, if I take the average of this function, E has a cosine term, B has a cosine term. We're going to take the average of cosine squared. What's the average of cosine squared over a period?
1/2.
1/2. And so this is going to be equal to E max, B max, over 2 mu naught. But we can rewrite it other ways because of this relationship. And this is where we get all the equations. Okay, we can also write it in terms of E squared max over 2c mu naught. We can also write it as c b sub m squared over 2 mu naught. We can also write it as U total average times C. So the intensity could be written in many different ways. Generally, in the homework, you're just plugging numbers into an equation. Okay, so now we've talked about characteristic of waves. Let's do a problem. This is this is an important problem because it gets you to understand the basic characteristics of a wave. So make sure you understand how to do this one. And there's one in the homework like it too. Although the way I stated this problem, there isn't ambiguity in the problem, and that's deliberate. Okay, so we have electromagnetic wave F is 10 to the 8th hertz. The electric field, the magnitude, is 50 volts per meter, or 50 newtons per coulomb. And E is perpendicular to the z direction. Wave travels in minus x direction. I want to write everything I can about the wave. So first thing is, what is omega? Well, omega is 2 pi times the frequency. What is the wavelength? Well, C equals F lambda. So that means that lambda is C over F. Wavelength is 3 meters. What's K? K is 2 pi over lambda. Let's see, what else can we figure out? B max. (50 volts per meter divided by the speed of light) is 1.67 times 10 to the minus 7 Tesla. So I know omega, I know C, well, I know lambda, I know K. I can write the equation for E. And I'm going to put the explicit value of K and X. So K is this guy. Do I put a plus or a minus here?
A plus. A plus, right?
Okay, yeah, put a plus because it's traveling in a negative x direction. And what do I put for the direction of the electric field?
Would that be? Oh, sorry. Would that be the plus or minus? Would that be the plus or minus j hat direction?
Yeah. So the problem is ambiguous, right?
Yeah.
Let's pick the plus j hat direction. So really, there's two sets of answers, right? I mean, I can choose the plus j hat direction, or I can choose the minus j hat direction. But that's going to affect me. That's going to affect B, though. Once I choose this, that's going to make me choose B. I cross J cross K is I hat, so this has got to be in the minus K hat direction. If this was in the minus J hat direction, then this would have to be in the positive K hat direction. Now I want the total energy. Actually, I want the average energy density, so I want U total average.
Professor?
Yeah.
I understand energy density. At least I thought I did. But how is energy density different than average energy? Just because, like, on the homework, it would ask for the average, or sorry, it would ask for the energy density, but I would use the average energy equation and would get it right. And I was just curious as to why.
Right. It wants the. You want the average. There's a difference between. Well, there's a fundamental difference between the average energy density and the. I got mixed up now. Which one? Which ones were the two you're asking again?
They asked for energy density.
So that's the energy per unit
volume.
Volume. Okay.
That's what I thought, but then I used the average energy equation and got it right, and I didn't know why.
The average energy or average energy density?
Average energy, just like that U total average. I can come in because I'm coming in a minute to ask you another question. I can just show it to you.
Yeah, because that's weird. I mean, from dimensionally, they're totally different, right?
Yeah, and I was stuck. We were stuck on it for a while because I kept getting the right answer, but the units were off. So I didn't know. Maybe I just missed a step or something. But I'll come in. I'll come in.
Okay. Oh yeah, come and show me. Okay. I want to find the average energy density. So I can write U total this way. Or I can write it either way. The average is going to be half of this. And so, well, the average is going to be half of this, and this is going to be E max. And just to save space, I'm not writing the units. Sorry. And this comes out to be, I have to look up the answer. 1.1 times 10 to the minus 8 joules per meter cubed. And then the pointing vector, it wants the average pointing vector. Oh, it's going to be this, sorry. Let me write it this way. And this is going to come out to minus 3.33 joules per, or let's do it in watts per meter squared. When I take the average of E cross B, I'm going to get the 1/2 out. Questions on this? Okay. Suppose we have a source of waves that's spherical. And it's like when you take a pebble and drop it into a pond, you get a bunch of circles, and as the wave travels outward, the circles get bigger. The energy in each one of those circles is the same. The energy is distributed over a larger surface area, but the wave travels outward. So as the wave travels outward, the energy is distributed over a larger area. This is why the idea of the intensity is important. The intensity is the energy per unit area per unit time in a wave. The spacing, I didn't draw it very well, the spacing between the circles is the wavelength. The circles are called wavefronts. They're basically points in the wave that are in phase. Right? These could be all the peaks of the waves. Okay? And these are called spherical wavefronts. And so this represents, if you're looking from the top, it just represents these waves. So if you're looking at the wave can also be represented this way. I didn't draw that very well. It can be represented in terms of an oscillation or something like this, a spherical wave. Now, as you get further and further away from the source, the energy gets distributed over a larger area. That's why we define the intensity as the power, the average power per unit area. And we're talking about the area of the sphere. All the problems we're going to do, we're going to assume spherical surfaces, okay? If I have a detector here of area A, and I wanted to measure the amount of energy per unit time absorbed by the detector, it would be this intensity times the area of the detector. And P average is the average power of the source. Now I want you to think about this, because we've been saying that the amplitude of the wave, we're representing the amplitude of the wave as constant, but really not. We can really rationalize why it depends on 1 over r. As this wave goes outward, the energy in one of these waves is the same, but the area increases r squared. Okay? The intensity, then we say, because P average depends on E squared, this is proportional to the amplitude squared. The squared electric field. And we're saying it's constant, but it really can't be. Because the area depends on r squared. Okay? The area depends on r squared. In order for the energy to be constant along this sphere, the amplitude has to depend on 1 over r. Because the area depends on r squared. So we can use this to argue that the amplitude of the wave really has to depend on 1 over r. We're ignoring that because we're really far away from the source. And if you had a cylindrical wave, then the amplitude would actually have to depend on 1 over the square root of r. Because the surface area of a cylinder just depends on r. But the amplitude depends on the intensity depends on the amplitude of electric field squared. Okay. All right. Let's do a problem. Suppose we have a distress beacon emits a wave at some wavelength lambda, and the distress beacon has an average output of 25 watts. So we're given a P average. What is the amplitude of the electric field 25 kilometers from the beacon? Well, I is equal to 25 watts over 4 pi times the surface area of the square of the sphere that's 25 kilometers. 25 kilometers is 25,000 meters. And that's S average. And we can write S average a bunch of different ways. So let me go back a couple slides. We can write S average as E squared M over 2C mu naught. And all I got to do is solve for this. EM squared is going to be equal to, I'm just going to bring this stuff up here. That's E squared, and then to find E, I take the square root of both sides. And I get 1.5 times 10 to the minus 3 volts per meter, or newtons per coulomb. Okay, see how much time I have left. Not that much time. I want to do a problem. I want to talk about, say a couple more things about the Poynting vector, and then I'm going to have to just say something about momentum. I never get to the point where I actually can justify the equations for momentum, but that's fine. And it could be because I do too many examples. Suppose I have a cube Or let me draw an imaginary cube, not a real cube. Sorry. And I'm going to use this corner of the cube for my axis. So one edge is at the origin of this thing. Okay? And let me define my coordinate system. X, Y, and Z. Each dimension of this cube is L. I have an electric field that's parallel to the y-axis. So I have an electric field like this. Okay? And I have a magnetic field. That's going to be hard to draw. It's in this direction. I want to know what is the rate, what is the energy flow out of the cube? What is the rate at which the energy flows out, in or out of the cube? It's a uniform electric field, a uniform magnetic field. The amplitude is the same everywhere. I want to know the energy flow. Well, in order for me to figure out the energy flow, I got to calculate the Poynting vector. Well, which direction is the wave traveling? Which direction is the wave traveling? What's J cross I? What is J cross I? Does anybody know? Isn't it the minus K direction? So this is going to be so this is going to give me so the energy is flowing in the minus Z direction, the energy flowing downward. How much energy flows through this surface? So the energy is going to go this way, right? Energy is flowing downward. This is the normal to the top. This is the normal to the bottom. S is this way. So top surface the energy flow is S dotted with N top times the area. And I multiply by the area because E is uniform, E and B are uniform over the area. If it wasn't, then I'd have to set up an integral. Oops. The dot product gives me -1. Bottom surface. Energy flow is the dot product of S with N bottom times the area. And again, since the pointing vector is uniform, I don't have to integrate over the area. And that's going to give me and I should have worked the average value so I wouldn't have to deal with this darn term. So what is the total energy flow through this volume? What is the total energy flow through the volume?
Is it not the sum?
It's a sum. And what does the sum give you?
Does it give you 0?
Yeah, so total energy flow is 0. Write it in words. What I've just calculated is this. That's the total energy flow through a closed surface. And I've shown that it's 0 for this case. If it's not 0, that means the system is losing energy. If I want to calculate the energy flow out of the surface, if it's not 0, then it's got to be equal to the rate in which energy is lost from the surface. So in this case, du over dt is 0. All right? This is the energy flow out of the surface because we define the normal as pointing away from the surface. If it's not 0, that means the system is losing energy. And so that's got to be equal to minus du dt. That's a capital U. And I'm not going to have time to do this problem. I would have loved to do this problem. I wanted to consider a charging capacitor. What happens when a capacitor is charging? And you know, because of the displacement current, there is a magnetic field between the plates of the capacitor. It's in the same direction as the magnetic field around the wire. It goes around the wire. The electric field is pointing downward. If you take the cross product of the magnetic field and the electric field, you'll find that the pointing vector points radially inward towards the center of that capacitor. The energy flows radially inward as the capacitor charges up. My goal in this problem was to show you that the rate at which energy is gained is equal to basically du dt. I was actually going to show you explicitly, but I couldn't because of time. So that couple of things about that capacitor problem. I was going to actually show you that it was really du dt here, that it's actually minus du dt. And I was going to show you that S points radially inward. You would think that the energy flows in the direction of the current, but it does not. It flows radially inward. Just calculate the pointing vector, and you'll see that. That's a surprising result in this problem. Okay. And if you had charges in between the plates of the capacitor, you would also have to take into account the work done on those charges. And so you'd have to actually add an extra term, which we won't talk about because we don't have time. I do have that in one of the in the next slide, but I won't get into that. I want to show you one more thing. By the way, any questions about this?
No.
Okay, so one last thing, and this always happens when I talk about this topic, is momentum. Electromagnetic waves carry energy, linear momentum, and angular momentum. When electromagnetic waves hit a surface, they'll transfer energy and momentum. So when light hits a black body is something that absorbs all the energy. It absorbs all the electromagnetic energy. Then one can show that the change in momentum of the object depends on the energy that's absorbed. And you can show that P is the total energy over C. When light hits, and this is normal to a surface, which is usually what you do in problems. This is a black body. A black body is something that absorbs any kind of light, radiation. If you have a perfect reflector, then the light hits the surface and then it gets reflected back, and the energy transferred is twice that. Oops. And I mention these because in the homework you have a couple questions on this. One can also calculate the radiation pressure. And again, I'm not going to derive, the book doesn't really derive these. You can also calculate the radiation pressure, which is essentially 2 times the pointing vector, the magnitude of the pointing vector over C. Okay? And this is where because of time, I usually give you the equations, and then most of the problems are plug and chug. The force per unit area delivered by electromagnetic radiation. Any questions?
I was curious how long you're going to be on campus today.
Maybe till 3. Tyler will be here till 4:30.
Okay.
I have to go to the bookstore. And I mean, I do have to run 1 or 2 errands on campus, but I'll be around. Tyler's here anyway.
Because I'm on campus now, and I'm just gonna finish up some things and probably head over to your office in about an hour and ask a few homework questions. I just didn't know if you would still be there.
Yeah, I'll be here. Well, if I'm not in my office, I'm probably at the bookstore.
Okay, I'll just wait then.
Okay. So, I mean, yeah, you could just wait around for me and I'll be here.
Okay.
Okay?
Cool.
All right, so I'll see you folks either tomorrow night during office hours or on Friday.
All right. Thank you, Professor.
Sure, no problem.